Thank you so much for joining us today. My name is Alex Spiridonov, and I'm the Director of Product Management for our Google Cloud TPUs. Can I get some cheers for TPUs? All right. That's better. Very happy to be here today with my colleague Mohan, who leads our Cloud TPU infrastructure and platform experience. And we have a very special guest today, Harris, from Citadel Securities. Can we show some love for Citadel? All right. Thank you. Today, we will talk about how we are fundamentally transforming the Cloud TPU experience to help you unlock unprecedented scale, reliability, and efficiency for the cutting-edge AI workloads. We have a great session for you today. First, I'm going to kick things off by talking about the incredible momentum we're seeing with TPUs in the market. Then Mohan is going to do a deep dive on the advancements that we're bringing to the Cloud TPU platform experience. He'll walk you through our new consumption models, our unified observability tools, and our enterprise-grade reliability features. And then finally, Harris will give you a real-world, under-the-hood look at how Citadel Securities is using this infrastructure to drive exceptional ROI for high-performance financial modeling. We have a lot to get through, so let's get started. Let's begin by looking over the evolution of TPUs and how TPUs are expanding beyond massive Gen AI pre-training to power the entire AI journey, including reinforcement learning and ultra-low latency inference. Now, as you know, Google's journey with AI silicon started all the way back in 2015 with our inference-focused accelerators. And since then, we have constantly been pushing the boundaries of scale and performance. Our latest TPU, Ironwood, the 7th generation, is now generally available. And it delivers 5 times the peak compute and 6 times the memory of its predecessor. But we're not stopping there. As you saw yesterday, we have unveiled the 8th generation TPU, purpose-built for the agentic era. TPU 8T supercharges ultra-scale model training, and TPU 8i does the same for reinforcement learning and ultra-low latency inference. And all of that adds up to powering your AI agents so that they can perceive, reason, and act with unprecedented performance and reliability. And this pace of innovation is exactly why the world's leaders of AI, like Citadel Securities, are using TPUs. As you know, foundation model builders, including Anthropic, are pushing the frontiers of AI innovation. We're not stopping there. Innovators across all industries, from global enterprises to cutting-edge startups, are also using TPUs to accelerate the entire lifecycle, from pre-training to RL to serving. And specifically, Harris will walk us through how TPUs are unlocking unprecedented ROI for Citadel's use cases. Now, I want to address a lingering myth that's out there that TPUs are only great for massive scale Gen AI pre-training. Now, it's true, they certainly excel at that use case. But the reality is that TPUs are engineered to accelerate every stage of your model development lifecycle. And yes, for training, we deliver near linear scaling at unprecedented cluster sizes. For example, the engineering team at Kakao unlocked a 2.7x performance increase for their models and vastly improved cost performance. But as the industry is shifting to post-training and reinforcement learning, demands change. And what we see is that TPUs also excel at things like multi-objective reinforcement learning and optimization, thanks to system and hardware innovations like our board-fly network topology and our dedicated sparse cores. And our software stack makes it very easy to use TPUs for those advanced use cases. That's why innovators like Escalante are using TPUs and seeing a massive 3.65 performance increase. And finally, with serving, when you move to inference, we pair our memory-centric hardware designs with industry-standard frameworks like VLLM. And so customers like Spotify are getting up to 3x better performance with near zero developer friction. But delivering cutting-edge hardware is only half of the story. To really unlock that performance, you need a world-class software and platform experience. So today, I'm very excited to announce a paradigm shift in our Cloud TPU infrastructure and developer experience to power developers and infrastructure admins with unprecedented flexibility enterprise-grade reliability, and deep observability. And to tell you more about those innovations, please welcome Mohan.
Thank you, Alex. We laid out a vision for TPUs that's staggering. From massive leaps in Ironwood to the specialized future of 8th generation TPUs we announced yesterday, the engine of AI has never been more powerful. But the true value of TPUs is not in its peak flops. It's in the results it delivers for your business. Even the most powerful engine, it's only as good as the control the driver has over it. To help you move from experimental to industrial scale AI, the hardware performance must be matched by equally powerful platform experience. If the hardware is the engine, the consumption experience is the cockpit. Today, I will walk you through a fundamental shift in Cloud TPU experience. We're going to pull back the curtain on some of our key innovations beyond hardware. So let's dive in. It all begins with access to capacity. The power of TPUs only matters if you can get your hands on them exactly when your business demands it. We're all familiar with the standard cloud models: on-demand for agility, reservation for guaranteed access, and spot for cost. While they serve their purpose, we wanted to offer something that's more aligned with how you actually work, especially for AI/ML workloads. First, for tasks like fine-tuning, reinforcement learning, and batch inference, we have Flex Start VMs. This is a game changer for mid-size workloads, offering up to 50% savings while providing a 7-day uninterrupted runtime. It's about giving your teams the runway to experiment at scale. And for your massive hero training runs, the projects that define your year, we have introduced calendar mode. You can now secure capacity for a guaranteed start time up to 90 days in advance. This turns infrastructure from a variable to a certainty. By making access flexible and predictable, we ensure that when your team is ready, the infrastructure is already there waiting for you. Now that we've secured capacity, the next step is choosing how you want to provision that capacity. We offer two options: the Cloud TPU VMs for virtualized and streamlined cloud experience out of the box. And for those who require direct unvirtualized control, we're announcing TPU bare metal starting 8th generation. For teams operating at the frontier of AI, we recognize that you need to get even closer to the silicon. TPU bare metal provides unvirtualized direct hardware access. By removing the Google hypervisor, we're enabling uncompromising stance for your most secure and sensitive IP and model data. But this is as much about speed as it is about security. Bare metal gives you direct access to low-level hardware controls, allowing for the kind of deep performance tuning needed to fully saturate the powerful infrastructure for your specific use cases and your model architectures. You have maximum flexibility to bring custom OS kernels and specialized hypervisors, tailoring the environment to your specific needs. Lastly, we have maintained operational parity. You get this raw control while still provisioning through the standard GCE API, GKE, and Vertex AI. We are giving you the keys to the hardware without adding any friction to your operational stack. Now, to manage this capacity at scale, we developed two modes to suit your specific needs. The first is the manage mode. In this mode, Google manages the physical infrastructure, abstracting away the nitty-gritty from you so you can fully focus on what you do best, whether that's research or running inference at scale. We handle automated repairs with strategic holdbacks to ensure your workloads stay resilient. For large and sophisticated customers who want to take the wheel, we launched Advanced All-Capacity mode. In this mode, you get dense reservations, physically co-locating your TPUs to minimize the latency and improve communications. You get full topology awareness, giving your engineers granular placement controls to map workloads to the physical hardware layout for maximum efficiency. You get advanced maintenance controls, so you can schedule system updates around your workload schedules. And finally, this physical access enables you to do dynamic slicing, which I will cover next. Whether you want the managed reliability or the surgical control of all access mode, we are providing the foundation for you to build with confidence. Before we go deeper into dynamic slicing, it's helpful to ground ourselves in the architecture of the TPU pod. What you're seeing here is part of an Ironwood superpod, which consists of 9,216 chips in total. The entirety of the single superpod it doesn't fit on the screen at this scale. It's too huge. The superpod is built from modular units that we call cubes. Each cube is a 4x4x4 cluster of 64 TPU chips, roughly the equivalent of a single rack shown here. Within this cube, all TPUs are interconnected with interchip interconnect or ICI to ensure lowest possible latency. But the real architecture breakthrough lies in how these cubes are connected to one another. We extend ICI through Google's own optical circuit switch, or OCS. Because this interconnect is optical, we can reconfigure the network paths in real time without trading off latency or bandwidth. The Ironwood superpod has what we call 3D torus topology. If you picture each of these cubes as a 4x4x4 3D, the real capability here lies in how you can assemble and reshape them to fit your needs. You can create slices tailored to your specific workload requirements, starting from 4 chips and scaling up to massive slice sizes, including multiple cubes. Crucially, every slice you create, regardless of the size, maintains this 3D torus structure. We are exposing this physical topology and raw flexibility to you through the advanced all-capacity mode. So, how do you translate this physical flexibility into actual velocity for your teams? Traditionally, starting a large-scale AI job required an all-or-nothing wait for VMs to be created and then network links to be formed in a single massive step, causing long lead times. Now, we have decoupled the VM provisioning from the slice configuration. In this new model, you provision all your capacity first as VMs, or in the case of GKE, as node pools. With the VMs in place, when you have a workload, you can stitch the resources together into the exact topology that you require, and together forming a slice. The system leverages ICI and OCS connectivity to make the shape come alive. By separating these steps, you can achieve more than 2 times faster job startup times. This ensures that your infrastructure is responsive and keeping pace with your ambitions. But where dynamic slicing truly shines is in its approach to resiliency. Now stay with me here. What you're seeing is an 8x8x8 TPU slice with all the network links active. Once you strip away the OCS connections, this is essentially made up of 8 cubes. You're seeing 4 of them in the front, there's 4 in the back. When you're operating at the scale of thousands of chips, hardware hiccups like a single faulty chip or an ICI link issue, that becomes a reality. Traditionally, such failures would have caused disruption to your workload and required you to reform the entire slice. With dynamic slicing, you can swap out an entire cube with a healthy spare using OCS reconfiguration while keeping the 3D topology of the entire slice intact. This reduces the mean time to recovery by 5 times compared to what it would take on the traditional path. That brings us to reliability. To lead in the AI era, you need more than just fast chips. You need a platform that ensures progress at a massive scale. With Ironwood SuperPod, we are operating at the scale of 9,216 chips in a single scale-up domain. That's more than 100 times larger than what is available anywhere else in the industry. At this level of complexity, the traditional single VM uptime doesn't cut it. The success of large-scale jobs depends on the collective performance of the entire cluster. That's why we're introducing cluster-level reliability. We are bringing the exact same rigorous standards that Google uses internally to train Gemini and other most advanced models directly to your workloads. We are shifting the focus from individual instances to ML goodput or overall cluster efficiency. We are setting a new standard that at least 130 out of 144 cubes are fully active and connected 95% of the month. And for those of you running smaller scale jobs with multiple replicas, and care about how many hosts, this extends to 99% of the hosts within a pod at any given time. That's over 9,100 chips. This is over and above the 3.9 single SLA that we provide for managed capacity. The innovations that we have seen, like dynamic slicing and software resiliency features, only add on top of this infra reliability. Now, as we scale to thousands of chips, the full stack observability is more than a feature. It becomes your critical operational tool. We built an ecosystem that gives you total transparency, starting deep at the infrastructure layer. Through our newly upgraded monitoring library, we provide extensive telemetry on your infrastructure, from fine-grained and core insights like TPU duty cycles, HBM utilization, all the way up to ICI link health. Crucially, we are providing fleet efficiency and goodput metrics. Instead of just focusing on your infra uptime, these metrics tell you how much of your capacity is performing productive ML work versus idling. By exposing these signals through multiple channels like the SDK, cloud monitoring, and integrated dashboards, we are giving your platform admins the data they need to ensure that the infrastructure is always performing at its peak. But infra observability by itself only takes you so far. For ML engineers and researchers, you need to have a workload-centric view. And we are pushing the frontier here. Through our ML diagnostics platform, we are delivering a managed end-to-end experience for workload profiling and monitoring. It effectively answers the age-old question, is it my code or is it infrastructure? In the next few slides, we'll see how this managed experience is helping our customers. Let's go. As an ML engineer, I wake up in the morning, it usually starts here, the run summary. Every ML run created through SDK, CLI, or workload monitoring UI is listed here. I have a clean, searchable history of my ML runs, complete with orchestration details and other metadata. When I click into an ML run, before I even look at the loss curves, I can verify the environment. I can see the software stack, the exact TPU topology, the run details, and the status all in one view. It gives me the confidence that my ML run is running in the environment that I intended, saving me hours of debugging on silent configuration errors. Now, I want to look at the performance metrics for the run. Here, I'm looking for consistency. Is my step time stable? Is the throughput where it's supposed to be? I can see the heartbeat of the training run here. If there's a spike in step time, I don't have to dig through the logs. I can see the regression immediately on this dashboard. But a performance degradation could be code or it could be hardware. Here's where system metrics play a huge role. I'm seeing the hardware pulse. We are pulling signals directly from libTPU on HBM utilization, the TPU duty cycles, and host CPU and memory. If my duty cycle drops and the HBM stays flat, I know the hardware is waiting for my code, not the other way around. Now let's say I do find a performance bottleneck or performance degradation. Historically, this is where things got really painful. Setting up a profiling for massive TPU cluster usually was so much work that many teams skipped this deep profiling until they ran into issues. We wanted to change that. With our managed profiling, that friction is gone. While these views are not always on, to save overhead, profiles can be easily captured programmatically through SDK, captured on demand through CLI, or through this UI very easily. I can tell system which nodes to profile, and the platform handles the backend orchestration, capturing the trace in a managed environment for me to analyze immediately. Once the profile is captured, now I'm in the trace viewer. This managed mode can handle even the most massive multi-node profiles. I can see exactly how the XLA is scheduling operations across the cores. I can identify fusion opportunities and memory stalls. But most importantly, I can share a direct URL of this specific trace with my team so we can debug together. ML diagnostic platform with end-to-end performance, optimization, and managed profiling is now generally available. But I can't watch dashboards 24/7. This is where workload monitoring becomes my silent partner. For every GKE job submitted, there is an ML run automatically created, and the TPU duty cycle across my workload will be monitored automatically. It's constantly running background analyzers to detect bad states, like a sudden drop in throughput. It correlates these states or drops with infrastructure events on a single timeline, so I can see exactly if a hardware event triggered my training stall. Finally, we don't just tell you the problem exists, we help you fix it. The system provides suggested actions. If a specific node has an issue or an ICI link flap, the platform tells me exactly which host is the culprit and suggests a remediation, like outcasting a node or restarting a job. It takes the detect and diagnose cycle from several hours down to minutes, ensuring you stay focused on the workload, not the plumbing. Workload monitoring is now available in preview today. The new Cloud TPU experience is more than just a collection of features. It represents a fundamental shift in platform experience of AI infrastructure. Now, the success of a platform, it's only truly defined by the world-class innovations it enables. To show you what this looks like in one of the most high-stakes, data-intensive environments, I'm thrilled to welcome on the stage Harris Nair, Head of Research Platform Infrastructure at Citadel Securities. Welcome, Harris.
All right. Well, thanks, Mohan and Alex, for the introduction. My name is Harris Nair. I'm the Head of Research Platform Compute here at Citadel Securities. So as Alex mentioned, TPUs are not just for the Gen AI companies. And hopefully over the next 20 minutes or so, I can show you a little bit how we here at Citadel Securities have been able to leverage TPUs to really transform our business. So with that, let me start by introducing Citadel Securities. We are a global market maker operating one of the largest trading platforms in the world across equities, options, and fixed income. And just to give you a sense of the scale, our platform executes over $500 billion in total value every day, including nearly 1 of every 4 trades in the US equities market alone. And at the core of every trade, really powering the success of our trading platform, are our quantitative models, allowing us to price assets, evaluate risk, and predict the direction of markets, all within fractions of a second. Now, the real challenge here, it's not just about having an accurate model of markets. It's really about being able to, in real time, adapt and retrain those models as markets evolve, and scale those models out across hundreds of different exchanges and asset classes. So that's really where our research platform comes in. At a high level, you can think of this as the infrastructure that connects our researchers, right, the quants at Citadel Securities, to the large-scale compute and data they need to train and evaluate their models. So on the left here, we have our quantitative researchers, right, responsible for developing new models, running back tests and experiments, and eventually deploying these new ideas out onto our production trading system. Skipping over to the right here, we of course have Google Cloud, providing the scale-out compute and petabyte-scale data management, really providing the cloud infrastructure that allows us to train and evaluate these models. And then in the middle, my team operates our research platform. And you can really think of this as the key layer of abstraction between the two. Our goal is to provide a seamless interface for our researchers without them having to worry about the complexity of managing infrastructure at scale. Right? We really want our quants focusing on financial markets and models, not the underlying infrastructure that powers them. So here's a bit of a deeper look at what that might look like in practice. So we'll again start with the researchers here on the left. They're going to define their models and workloads generally directly using JAX, along with the set of Python packages that my team provides. And they'll then submit those workloads to our backend research platform. Once a workload is submitted, researchers can log into our research platform UI, monitor the progress of their jobs, tweak parameters, analyze results, and so on. On the back end, everything else is handled by our platform. We orchestrate the full lifecycle of every workload, covering things like job scheduling, right, when and where workloads are executed, resource provisioning, dynamically provisioning compute resources using the Cloud TPU APIs that Mohan and his team provide, data management, so we leverage Google Cloud Storage to efficiently load market data, and so on. And really, the key point I want to make here is, our platform is tightly integrated with Google Cloud, but that cloud infrastructure and complexity is really abstracted away from the end user. Right? Our goal is to provide a single, unified cloud research platform. All right, so as we saw on the previous few slides, right, from the researcher's perspective, we provide this simple and seamless experience. But obviously, behind the scenes, there's a few core platform challenges that we need to think about. So first, we have hundreds of researchers with diverse use cases. Right? Our workloads range from small-scale experiments all the way up to massive market simulations. And we really need to be thoughtful that our platform is performant at anything our researchers might throw at us. Secondly, our platform needs to support thousands of concurrent large-scale workloads. Really being able to scale up our computational power to meet that demand is absolutely critical. Third, just by the nature of research, right, it's highly unpredictable and interactive. And that makes our research demand bursty and latency sensitive. Right, our researchers expect fast iteration cycles regardless of their workloads, and that presents a real challenge in how we're able to manage capacity. And then lastly, all of this is operated by a lean platform team. And what that means is our platform needs to be highly automated, it needs to be easy to maintain, and it needs to be reliable at scale. All right, so given these challenges, right, the question really becomes, how can we address these? And for us, that's where we found TPUs really to be a very strong fit. And there's basically three reasons why. First, TPUs offer efficient scaling for large distributed workloads like ours. Right, what we'll see over the next few slides is that this unique torus architecture that Mohan discussed earlier really allows for more efficient and simpler scaling on TPUs compared to more traditional accelerators. Second, TPU offer flexible capacity for satisfying compute demand. Right, as we discussed, we have highly bursty and latency-sensitive workloads. A fixed capacity model is simply not going to be sufficient for us. And we'll see in the next few slides how we can leverage some of the consumption models that Mohan discussed earlier to really address these challenges. And then lastly, the TPU ecosystem provides fleet-wide observability and monitoring. Right, the diagnostic suite that Mohan showed previously has been absolutely critical for us when running at our scale. And in the next few slides, we'll see a couple examples where we've been able to really invest into that to quickly identify and triage issues at our platform. So there's really three key aspects of the TPU environment. Right? It's efficient scaling, flexible capacity, and fleet-wide observability. And we'll talk more about each of those in the next few slides. So with that, right, given how critical performance is for our platform, let's start with a closer look at the first point here, right, efficient scaling, and really see how TPUs are able to do this so effectively. At a high level, the key difference comes down to how the system is connected. Right? It's about the underlying network topology. So what we're seeing here on the left is our traditional GPU cluster. We would typically have what we call a hierarchical network design. And what that means is that communication within our cluster happens across multiple network layers. Right? We have high bandwidth connections within a node, lower bandwidth fabrics across nodes, across racks, and so on. And what that means is as we scale up this GPU deployment, the point-to-point communication between any two GPUs within this cluster for, say, some given collective, that point-to-point communication becomes increasingly unpredictable and complex. Right? We're now spanning multiple distinct network layers, right, and communicating across different network layers with different performance characteristics and trade-offs. And that kind of fragmentation and complexity inevitably leads to communication bottlenecks as we scale. In contrast, TPUs, right, here on the right, use what we call a torus-based network topology, where each chip is directly connected to its neighbors in this regular grid-like pattern. And what that does is it creates a much more uniform and predictable network. And it also means that as we scale up our compute capacity, right, as we add additional chips into this TPU cluster, we're also adding additional links and aggregate bandwidth to our overall network. Right, we're really able to scale up the communication and network capacity of the cluster as we scale up our compute. And that way, we're able to avoid these communication bottlenecks even as we grow our cluster. So here's an example of what that might look like on the workload level. So what we're seeing here in the graph is how the overall throughput and performance for our workload, right, that's the y-axis here, how that scales as we increase the number of processors here on the x-axis. So ideally, right, of course, what we would want to see is what we call linear scaling. Right? So as we double the number of processors, we're exactly doubling the throughput and performance of our workload proportionally. And that's very close to what we see in practice for TPUs. Right? As we scale up our TPU clusters, that's the green line in this graph here, as we scale up our TPU clusters, performance increases very, very close to ideal, right? Very close to linear. We're actually able to achieve over 95% scaling efficiency on the TPU cluster, even as we grow out to thousands of TPU chips. And that's really a difference from what we see from more traditional accelerators. Now, I don't want to make the point here that it's impossible to scale GPU clusters. Clearly, other companies have done so with success, but it can be more challenging, right? And it often means reworking and re-optimizing your workload at different scale points to really try to work around these network bottlenecks that we discussed earlier. Right, the real sort of power or beauty of the TPU architecture is that I can design a workload at a specific scale point, right, a specific number of processors, and really be very confident that as my model size grows, I'm able to scale that efficiently without actually re-architecting my workload. So here's what this really means for our business. Right, as we've evolved the structure of our workloads from these small and somewhat limited scale deployments on GPUs to our initial experiments on TPUs with v6e pods, to then scaling this out across multiple pods using multi-slice v6e, and now finally where we are today with v7 Ironwood, we've really been able to transform our research. Right, we're able to run workloads with over 10 times the model size we've had historically. And with TPUs, we're able to execute these workloads 40% faster and with a 30% lower cost basis. Right, we're really building much more comprehensive and accurate models today. And we're able to iterate on our ideas faster and cheaper than ever before. And that delivers not just a much better experience for our researchers and the end user of our platform, but also delivers a much stronger trading system for our clients and our overall business. So this is really an incredible result of migrating to TPUs. Now, to really be able to leverage that ability to scale workloads in reality, we need to back that up with real capacity. Right, and this is actually a unique challenge, right, particularly given what we said earlier around the bursty and interactive nature of our demand. And in practice, what we'll see is that we really need to leverage a combination of the capacity and consumption models that Mohan mentioned previously to really be able to manage the flexibility and availability of our capacity. So DWS FlexStart, for example, allows us to dynamically scale our TPU capacity, particularly for these unpredictable and bursty workloads. In the early days of our platform, this was an absolute key, right? It allowed us to quickly benchmark, and DWS allowed us to quickly benchmark and iterate on TPUs without necessarily locking ourselves into a financial commitment or a specific cluster size or topology. And now, as we've grown our platform, not just in scale, but in the business criticalness and impact of our workloads, we started to lean more into committed capacity. Right? That allows us to provide a reliable and guaranteed access to TPU with production-grade SLAs for our most business-critical workloads. So as we said, right, in practice, we need to combine the flexible and committed capacity and consumption models to really support the full spectrum of workloads on our platform. So this graph here gives you a sense of what that might look like. Right, we have our production workloads. These are our most stable, business-critical workloads that directly impact trading. Those are going to form the floor of our committed capacity, right, providing us with predictable and reliable access. And then above that, we have these bursty and unpredictable research workloads. Right? And there we can leverage DWS and on-demand to try to satisfy the peaks of that demand without necessarily over-provisioning on our steady state and committed capacity. And if you think about this from the perspective of our researchers, right, this is really solving their challenge. Right? They're able to sleep at night, knowing that we'll always satisfy the demand for their production-critical trading workloads, while still giving them the flexibility and freedom to freely experiment on new ideas and new models. All right, so we've seen how we can scale our workloads to meet our performance needs. And we've also seen how we can scale our capacity to meet our research and compute demand. The final piece here is really how can we scale our operations. Right, so Mohan showed this Google Diagnostic Suite earlier. I just want to focus on a couple key areas within that where we've really been able to invest and deliver key solutions for our researchers. So the first of these is around XProf profiling. So XProf is a profiler supported directly in the JAX and TPU runtimes. And with some simple integrations within our platform, we've been able to expose those profiles directly to our researchers. Right, so what that looks like is a researcher can log into our research platform UI, and with just a few clicks, right, see full and detailed profiles for any of their historical workloads, right, allowing them to very quickly debug and optimize their models. And the second investment we've made is around our fleet-wide monitoring. So Google TPUs provide a number of highly granular performance and health metrics. And we've been able to leverage the underlying Cloud TPU libraries to export those metrics directly into our internal monitoring systems. And what that's allowed us to do is to power not just dashboards, but programmatic notifications and alerts, all the way from visualizing the performance of a specific workload or a specific user, all the way up to critical platform-wide health and capacity monitoring and alerts. And really taken together, right, it's these kind of capabilities that allow us to operate our platform at scale. Right? As we grow our users and workloads, this kind of operational tooling becomes absolutely critical in supporting our platform. All right, so we've talked about the improvements we've been able to see in terms of scaling and performance on TPUs. We've talked about how we can leverage some of the different capacity models. We've also talked about our tool sets for observability and monitoring. So with that, I just want to close with a few key takeaways. So first, TPUs enable efficient scaling through this unique torus architecture. Right? More so than other traditional accelerators, TPUs are actually inherently designed to scale for the kind of large-scale distributed workloads we're running. And as we saw, right, that's really been a key differentiator for our business and our research platform. Second, it's not just about the hardware. It's really the ecosystem around it. And what I mean by that is by building on top of the entire Cloud TPU platform. Right, I'm thinking about the different consumption models or the diagnostic suite. Right, by building on top of that entire ecosystem, we're really able to expose the TPU hardware to our researchers in a way that is both very seamless for them, but also very powerful. And then lastly, I just want to end with not just the success we've had so far. As we've seen with TPUs, we're able to run workloads that are much larger, much faster, much cheaper, and much more reliable than we ever have in the past. But also looking forward, right? With V8 on the horizon and all of the features and capabilities that Mohan and his team are building out, we're really excited to see what the next iteration of our platform can really bring to the table. So with that, thank you, Mohan and Alex, for continued partnership. Thank you all for being here, and I hope you enjoy the rest of the conference.